Greetings everyone, this is not an expert here, back again with another video. Today we'll be solving problem number 23, and the difficulty it's been rated at is easy. This problem was asked by Google, and let's just look at the problem description. So you're given a n by n matrix consisting of booleans that represents a board. Each true boolean represents a wall and each false boolean represents a tile you can walk on. So given this matrix, a start coordinate and an end coordinate, return the minimum number of steps required to reach the end coordinate from the start. If there is no possible path, then return null. You can move up, left, down, and right, and you cannot move through the walls. You cannot wrap around the edges either, and you're given a representation of how it looks. And yeah, that's it. So there are actually a few ways of solving this problem. One of the ways is by using dynamic programming. But that's only with the constraint given that if you have a proper source and destination already given. Um, and we would have to do a lot of manipulation also there. So we're not going to go with that. What we're going to do is we're going to go with the breadth first search approach. Unfortunately, we were able to find a problem on LeetCode which is quite similar to this problem. You can pause this video and look at the link in the description below. But it's basically the same problem. If you're encountering 0, that means it's empty and you can go through that particular element. Otherwise, 1 sort of depicts that it's blocked or it's like a wall. Over here we are given an n by n matrix and not an n by m matrix, but that does not really matter, it's sort of irrelevant. And again, so the way to sort of go about this is just by using a simple breadth first approach. So let's just start. Before we start, we'll just start with our base condition, and our base condition is that what happens if our first element of our grid is already, it's blocked, it's 1. In that case, we return -1, right? If you didn't understand what this is, it's going to get a little confusing, but basically whenever we have a true value, that would mean that that's blocked. Whenever we have a false value, it would mean that's empty and we can visit that value, right? And we have an entire grid, so we can pass through that entire grid easily. Cool. Let's just make a quick variable. Let's make it length of grid. And also we'll make one more, which is basically the directions array. So if you having trouble in understanding what the directions array is going to be, so basically in our previous question we were given that we could go top, bottom, left, and right. Over here we are given that all elements or cells are connected 8 directionally. So basically we have to encounter all those things as well, right? So the directions is just going to be the ways that we can sort of go about it. So a quick way of sort of doing that is actually just making a 3 into 3 matrix, putting the middle element as 0, and then just plotting out all the indexes from there. I won't do that because that's just going to take a lot of time, but you can do that as well. So -1 0, we have going to have 1 1, then what else am I missing? -1 and -1 and 1 and 1 and -1. Cool. I think that's it. I think there's -1 and 1 also, which I'm missing out, which is going to be at the top. And again, you don't really need to worry about this too much. Hopefully I've got all the elements right. Let me just go 3 4 5 6 7 8, and yep, that seems to be good. If you're having difficulty in solving this, right, I'll just explain what I was talking about, the 3 by 3 matrix. Just make a simple matrix, right? And let's just make it a 3 by 3 matrix. So you have -1 -1, then you have basically what you want to do is you just want to say you have A, B, C, D, E, F, and G space H space I. So E is going to be the 0th element, and then you just plot, how will I go to A, how will I go to B, how will I go to C, D, F, G, H, I, and just depict them in in a tuple representation because you're at ij over here. So A for that example would be I -1, and j minus 1, right? So that's the way you sort of go about it, and that's the directions list. Cool. So enough of that. Let's just get to our actual approach, right? And the way most of the times you sort of use um, BFS is actually by using a queue. And let's just make a queue. We're going to import it with our DQ model. And basically what I'm going to do is I'm going to make sure that inside this value, there are a few things. So what we know for a fact is that we're going to be starting our source element is going to be 0, 0. So basically a queue is going to contain a few elements, and each element inside our queue is going to have the ith value, the jth value, and the cost, right? And we're just going to keep on pushing it there. We're going to also have something called as a visited hash map or set. It's just to maintain whether we've already encountered this ij value, and if we have, we don't really need to worry about it. We don't really need to consider it anymore, and then go forward from there. Cool. So let's do a quick BFS implementation. BFS implementation, and the way to do a BFS implementation is by pushing a value inside your queue, popping out all those values one by one, and run it on a while loop. And while running it on a while loop, you sort of do all the computations on that particular element. So and it's a little difficult to track it, but let's just move on with it. So what we're going to do is we're going to pop out the value. So let's just pop out the first value which we have in our queue. So we're going to do pop left, right? And let's just extract ij and cost from val, right? And all we have to do is we have to first check whether I is equal to j and whether they're equal to n minus 1. In which case we just need to return the cost, which means that we've already encountered this thing, we've reached the end or the destination. So whenever that happens, we just return it and break out of the loop and just return the output, right? And the next thing is we're just going to um, run this queue, whatever element that we are on, and run it for all directions, all possible go to from there, right? And the way to do it is by using the directions list that we've made. So we're going to do for x comma y in directions. All we have to do is we just have to set a new element. So let's just call it nx, and that's just going to be whatever I plus x is, and ny, which is the next y value, which is j plus y, right? So you're at I and j right now, and all you're doing is you're just iterating through it through all the directions, right? So this will go top left, bottom right, top left, top right, all those things. So this will give us all the nx values, all the indexes that we need to go on, and all we have to do is we just have to check first whether these values are safe. And the way to check them is actually just an if condition, and the if condition is if they are less than equal to 0, they're not safe, or if they're greater than n, they're not safe, right? So we're just doing that. So if they are in that range from 0 to n, that means it's fine, right? So that's that. And oops, sorry. So let's just pull it down a little, and we need to check for whether the grid is valid. So the way the grid is valid is checked by whether it is a false value, right? So we do not grid nx, oops, sorry, nx and ny, right? Or you could actually do and equal to 0. Actually, we'll do that. That might be better for us. Let's do that. Let's do this thing. If it's 0, if it's an empty cell, then it's fine. And also whether nx comma ny is in our visited set, right? That means it's already visited. Um, oh, sorry, not in our visited set. If they're not in our visited set, then we can sort of move forward. And all we have to do is inside our visited element. So we do nx, ny, and that's it. Now we do that with the visited set. So If you don't understand how a visited set is taking a tuple inside, it's just an implementation, a hash implementation of how it can take a set or a tuple. It's very easy for it to do that. So we're just using that and we're just comparing it with that. So we've added it in to a visited so that we don't encounter it ever again. And we also append our value inside our queue. So we do nx, ny, and the cost will basically be +1. So the reason why it's +1 is because each element, each time you iterate through it or each time you go on it, just adding one value. And whenever it sort of encounters that value, it's just going to get returned. Whenever we sort of reach our destination, it's going to get returned. And yeah, and that's it. So all we've done is we maintained a queue, right, and a visited set. And every single time through a while loop, we just keep on popping the value, the first value rather, from the queue. We keep on popping it out and we keep on checking whether the number of iterations or the number of directions where it can go is correct or not. And we pass it through all the directions. So it passes it through all the directions wherever it can go. And over here, this is just a safety check whether the value is safe or not, or whether nx has not increased or ny has not increased or decreased and still within the range. And over here, you're just checking whether it's a valid tile or a valid number or a valid cell or something that you can traverse on. And then we just check whether it's not visited ever before, because if you're iterating through the same value which has already been visited, that's an issue because you can get into a loop, right? So we maintain that with visited, and all we're doing is visited.add, and we're just adding the indexes I and j to our visited hash map, right? And that's it. And we just keep on appending those values, and the entire loop keeps on running till we find I equal to j, which is equal to n minus 1. And that's basically it. So let's just try running this once. Hopefully this should run fine. On the basis of what complexity it's running at, it's basically running at an n square complexity. And the space is also n square. Uh, yeah, it's pretty self-explanatory, but yeah, and it seems to be running fine. Let's just try submitting it. Cool. So this is running fine. It's faster than 72% of the online submissions, and the memory usage, actually there's no memory which is used whatsoever. It's 100% better. Um, so cool. And that's basically it. So this is our approach of handling this problem, and the way to solve this problem is definitely by a BFS. I hope this was clear, and if you have any doubts, do leave it in the comments below. I would love to come back to you. Also, if you've not subscribed already, do subscribe to the channel. We are a discussion over here, and we'd love to have you. We're pushing videos on the daily, and it's going to be really cool if you're with us. Also, if you like this video, do give a like, and if you've already subscribed, you're awesome. We all know it, and have a great day. Thank you.